Welcome. This video is going to talk about chemical reactions and then contrast it with nuclear reactions and mostly focus on nuclear reactions. So chemical reactions involve the change of one or more substances into new substances. Atoms are rearranged, but the atoms' identities do not change. So this is what early scientists like Democritus and Dalton thought happened, and it's what scientists still believe happens in the reactions that go on around us all the time. These reactions involve the atom's electrons only, and this is what we're going to be studying the majority of the year in chemistry, or what's known as inorganic chemistry. Nuclear reactions, by contrast, involve a change in the atom's nucleus. An atom of one element actually changes into an atom of another element. The identities of the atoms do change. And they don't occur that often in nature because many atoms have already decayed. So if you maybe have heard of the term half-lives, because Earth has been around for lots of years, most of these reactions have happened. But there is still some natural radiation going on around us. Some of it's dangerous, but most of it's harmless. The carbon in us is constantly undergoing decay. The hydrogen that's in the water and everything around us undergoing some decay. So this natural radiation is often used to date old stuff, like if you've heard of carbon-14 dating, and it's used for treating some medical problems. So when you hear about people undergoing radiation, this is the stuff they're talking about. We also make nuclear reactions happen for generating electricity at nuclear power plants and for powering submarines, and then we also use it in an uncontrolled manner in nuclear bombs. So what is radioactivity? It's defined as the fact that some substances spontaneously emit radiation in a process called radioactivity. So what is that? Well, it's a process that requires no energy. It's not a process we can speed up or slow down, at least not easily. And it occurs because an atom's nucleus is unstable or overcrowded. There's either too many protons or too many neutrons or just too much stuff in the nucleus. Remember, the nucleus is very dense and very tightly packed, so there's a limit to how tightly packed a nucleus can be before it loses its stability. So it gains stability by losing energy or emitting radiation. And your book likens it to a pencil tipping over. If you had a pencil and you balanced it on the tip or even on the eraser, that would be very unstable. It would not take much of a disruption to make that pencil tip over. But a pencil laying down on the table, that's pretty stable. So an atom continues to be radioactive and undergoes decay until its nucleus becomes stable. Different types of radiation can be emitted during radioactive decay, but the three most common kinds are alpha, beta, and gamma. All three have energy, but only two have mass. And the process of emitting them is known as radioactivity or radioactive decay. The rays and particles emitted are known as radiation. And this is where Einstein got that whole idea of E equals mc squared, E being energy, m being mass, and then c squared is the speed of light. And what that really means is a small amount of mass or matter can be changed into a huge amount of energy. And let me just give you a graphic here of kind of what's going on with radiation. So you start with your atom. And I'm just going to put that this is an unstable nucleus in the atom. And this is the nucleus, the atom's nucleus. So remember, since it's a nucleus, it's filled with protons and neutrons. And something about the ratio of protons to neutrons is making this unstable. And what happens is just spontaneously some energy gets emitted, and at the same time, some kind of particle gets emitted. And that particle can be what we call an alpha, beta, and technically gamma isn't a particle. It's just energy coming off. But that's kind of the general process, is that this nucleus, a little piece breaks off, and that allows energy to be released. I want to talk a little further about stability, because stability is a big deal in both nuclear reactions and chemical reactions. It means a substance is unlikely to undergo further change because it's at a low energy state. So Stability and energy have what we call an inverse relationship. To be stable, substances need less potential energy. I see I'm missing my L there, but that's potential energy. So if you're standing on one leg or doing a handstand, it requires a lot more energy than standing on 2 feet. So if you look at both these graphics here, you know it would take a lot more energy by you to maintain either of those positions. So that's less stable. It'd be far easier for somebody to come and knock you over if you're in one of those positions. But if you're standing on 2 feet, or even if you're lying down, that takes far less energy, and we consider that much more stable. And then just to finish up, here's a radioactive decay series, and this just shows the yellow up in the upper right is uranium-238. And these are all the reactions, the nuclear reactions it has to undergo before it finally becomes stable lead-206. So you can see that radioactive decay can be a very long process. Other atoms, it's a much quicker process. It all depends on the isotope that's decaying.